In section 7.6, we previously talked about how we're going to do integrals, and we called them improper integrals. In this case, it's improper because one of the limits of integration is actually infinity. And the way that we adjusted for these or worked around that is we actually used limits. But before we get into that, let's just first talk about how we can find the general antiderivative, because that will allow us to eventually do this computation. So let's just figure out in general what 1 over x plus 2 squared dx would be. So I would start off first by rewriting that as x plus 2 to the negative 2 dx. And then applying our rules, that would be 1 over negative 2 plus 1 times x plus 2 to the negative 2 plus 1. And if we simplify that, we're going to get negative 1 x plus 2 to the negative 1. And dropping that back to the denominator to make it positive, we get negative 1 over x plus 2. So that's our general antiderivative. So we're going to use that when we do this computation. So we're going to swap that infinity out. We're actually going to do a limit. We're going to do the limit as b approaches infinity from 1 to b of 1 over x plus 2 squared dx. So we've already computed that general antiderivative, so this is going to be the limit as b approaches infinity using negative 1 over x plus 2. We're going to plug in 1 to b. So that would be negative 1 over b plus 2 minus negative 1 over 1 plus 2 would give us negative 1 over, and if we put infinity in for b, that's essentially negative 1 over infinity. Subtracting a negative, so plus 1 over 3. We get 0 plus 1 over 3 is 1 over 3. So that is actually the value of that improper integral. In section 7.7, we came up with some theorems, or we developed some theorems that allowed us to really quickly determine if something's going to converge or diverge, meaning can we find an answer for it. And so a few things I just want you to recall. That if you were trying to do, in general, an improper integral, let's say from a to infinity, and allowing a to be any number, of 1 over x to the p dx, that if you have something in this form, it will converge for p greater than 1 and diverge if p is less than or equal to 1. Okay? Then we had a few other theorems. Let's say 0 is less than or equal to f of x is less than or equal to g of x. Okay, so basically what I'm saying is f of x is less than g of x. So the f of x function is below g of x. If this is true, and the improper integral, let's say a to infinity of g of x dx converges. So in other words, if the larger function converges, then from a to infinity of f of x dx converges also. Essentially what that's saying is that the larger function converges, the smaller function must converge as well. The opposite is true too. Let's say 0 is less than or equal to g of x is less than or equal to f of x. So in other words, I'm saying g of x is less than f of x. And let's say this integral from a to infinity g of x dx diverges. Okay, so if the smaller function diverges, meaning we can't compute that area, then obviously the function that's above it must diverge also. So then a to infinity of f of x dx diverges also. Okay, so then I said, well, how do we know 1 to infinity of cosine of x over x cubed dx? Do we know if that converges or not? Well, we know since, let's say, from 1 to infinity of 1 over x cubed dx, because of that first thing that we talked about, because of this rule here, we know 1 to infinity of 1 over x cubed dx converges, and 1 over x cubed dx is going to be greater than or equal to cosine of x over x cubed. You're probably thinking, well, how do I know 1 over x cubed is always greater than or equal to cosine of x over x cubed? Well, cosine of x has the greatest possible value of cosine ever is 1, and its smallest value is negative 1. So cosine of x is always going to be less than 1, less than or equal to 1. And so for this reason, we can use this idea here. And so we now know from 1 to infinity of cosine of x over x cubed dx converges.